continuation of Kata that I started, I think, 2 sessions ago. So basically, if you weren't there 4 weeks ago, you're not going to understand anything, so you may as well leave. Now, actually, we're just going to review quickly what we did before. I made a couple of improvements to the code that we developed 2 times ago. But let me just remind you what this is about. What we're trying to do here is create a class library or a sample class library for mathematical logic, which is a permutation. And a permutation is just a rearrangement of n letters, if you like, a bijective mapping of the elements 1 to n to itself, the set 1 to n to itself. And a permutation can be broken down into cycles. Any permutation can. So for example, if you had a permutation of 5 elements, maybe you're just exchanging 1 and 3, and then maybe 2 maps to 4, maps to 5, and then 5 maps back to 2. And so that would be an example of a permutation that consists of 2 cycles. So on the one hand, we wanted to just build the basic functionality of a permutation class. And then second place, we wanted to write a function that would decompose any given permutation into the cycles that compose it. So we did the first part of that in the first kata. And I'd just like to briefly review the results. We're setting the size of our permutation class. I had done that before in a class variable. Now I'm using a class instance variable. You can see on the left that we are creating that implicitly by opening the class object and just using attribute accessor for size. And then we can reference that with p.size both inside and outside of class. We have an initializer where we can initialize the permutation by defining it as a function. So on the right-hand side in our test, we have several examples of that. We defined the identity permutation, which just sends every element to itself with a lambda. Similarly, we have defined a rotation permutation, which just sends 1 to 2, 2 to 3, and so on, and 5 back to 1. And then I defined another lambda here, just called it other, with a case statement which just maps each element to which one it mapped to. And those are 3 examples of how we could define a permutation with a lambda. And then what we've done is we've actually used that lambda as our data for the permutation, which to me was kind of an epiphany, maybe it was my crossing the line towards becoming a functional programmer. Because I started out with this trying to represent a permutation in a number of ways. Like you could represent a permutation as an array. You could represent it as a hash. It's kind of nice with the old Ruby syntax of hash because you actually have the little hash rockets there as arrows showing which element would go to which element. But then at some point I realized that this is a mapping we're defining from one set to another. It is a function. Why aren't we defining it as a function and representing it internally as a function object? So that's what we're doing. And it actually greatly simplified the implementation and compared to the way that I first tried to do it when I was trying to use an array internally to represent the permutations. So we have an initializer. We also built last week a way of creating a permutation from a cycle. We're actually representing a cycle as an array. So if we look at the test for that, where is that? I went by. Okay, so create from cycle. So we placed in a cycle 1, 5, and 2. And then we have a two-array method, which allows us to see what we got as a permutation. And as you can see, the third and fourth elements of the permutation are left unchanged. And 1 goes to 5, 5 goes to 2, and 2 goes back to 1, which is exactly what we asked for. And then we can also, I also added a method that we didn't develop the last time to create a permutation from an array of cycles. So there you see on this one that we're passing in a degenerate cycle that just sends 1 to itself, and then 2 other cycles that exchange 2 and 4, 3 and 5, and to get this expected result. And that is simply implemented by starting out with the identity permutation and then just calling reduce, passing in the identity permutation to start with, and then using composition to compose whatever we already have with the next cycle that's defined by the next array. So is that clear what's going on there? So that's going to be useful because when we decompose our cycles, when we decompose our permutation, we're going to get an array of cycles. And then in order to test whether we got the right thing, we'd like to be able to reconstruct the permutation from that array of cycles to make sure that we ended up with the right answer. I also added an equals override for our class, basically just comparing the arrays that are the array representation of both permutations. So my equals implementation, first of all, checks to make sure that P is actually an array. And then if it's an array, it checks whether self to array is equal to P to array. If that's true, then the result is true. So before we go much farther, maybe I have a couple minutes more here because the actual cycle decomposition isn't going to take too long. We last time created a compose function, and I used the star operator as an alias for compose, because you can compose 2 permutations. But I've actually changed that because there's a problem with using star as an alias for compose, which is that the star operator has a defined associativity with it. And you can override or overload the star operator, but you can't change the associativity of the star operator. And the star operator, which is typically multiplied, is left associative, whereas composition is naturally a right associative operation. So it's not really a very good symbol to use for composition, although it is widely used because there isn't really a good alternative. But what I did is I've actually redefined the star operator in this case by having F star G be G composed with F, which I think is actually more correct in terms of representing the associativity semantics of composition. But that won't affect us, though. What we do here. So let's jump into building this cycle decomposition. But I guess we ought to start out by making sure that the tests pass. So let's see. Here are our tests, and I'm using guard and rspec here. So I'm just going to type rspec here, and we're going to run 16 examples, and we have no failures, and we have 4 pending tests here. So in our cycle decomposition, I'm going to add another example here. I'm going to say it returns an array. Okay? And so we'll start out here. Remember, we want this to return an array of cycles, each cycle being represented itself by an array.
Now,
Yes?
you've got a syntax error on line 81. You need a space between the double quote and the D.
Oh, thank you. Okay, so then we're going to do, let's just take one of these permutations that we've defined, like we can use ROT. Rot.cycles is a array.
That's not a test yet. It'll just return false.
Oh, that's right, yes. Yeah, yes, we want to expect is an array to be true.
There's a better way of expressing that.
Yeah, what's a better way of that?
So we want expect rot.cycles dot two. And then you want be an instance of
Aha.
array.
Got it?
Yep.
Ready? It failed. Actually, let me just take a quick break here for grab some notes here, which I might want to look at later. So it looks like we don't have a method called cycle, so we'll fix that. And we'll put cycles, and we'll return an empty array. And now our test passes. Great, we're off and running. So now the next one is less trivial. Let's have it handle a rotation. Now, rotation is a single cycle. So that's an easy one to do. So we're going to expect that rotation.cycles to equal, and then we're going to have an array consisting of a single array element, 1, 2, 3, 4, 5. And that fails.
Can you make the font bigger in that?
Excuse me?
Can you make the font bigger in that turbo?
Oh, in the,
turbo.
yeah, how do I do that?
Command false.
Great. Okay. So now let's start to implement this. So we can start out by defining a variable cycles to be an empty array. And then the next thing we can do is we could take self to array to have something to work with. But let's give that a name, and we can call it. Let's just call it bucket, because this is kind of the bucket out of which we're going to have to be pulling our elements later. And we're just going to take one item at a time out of the bucket, figure out where it gets mapped to, and use that to build a cycle. So then let's start out by saying the next element is equal to bucket sub 0, right? And then we can start with a cycle, and we can say cycle is an empty array, and then what we can do is we can start out by putting what we call the next element into the cycle.
Two lessons.
Sorry?
Two
Oops.
lessons.
Yeah, we need two of these. And then we can make the next. Now we can redefine the next element to be equal to self, which is the permutation itself, applied to what was our next element. Okay, and then we'd like to put that into the cycle bucket, or sorry, that into the cycle array. But we need to do that in a loop, so we'll just put begin here. And then we basically want to keep doing this for a while, but we don't want an infinite loop. We want to stop when the cycle starts to repeat. So we'll say until the cycle includes the next element. Right? And then after we finished with our cycle, we then should add our cycle to the cycles array.
Two lessons.
Oops. And I think that's going to give us the right answer here. Let's see if it's true. And we failed. We got expected 1, 2, 3, 4, 5, but we got 2, 3, 4, 5, 1. Okay, so those are actually equivalent. Now, let's see here.
Why isn't that what you should have expected?
What?
Why is that not what you should have expected?
Well, it's the same cycle, but we want the cycles to be normalized so that they start with the smallest. So they represent they're starting with the smallest element of the cycle. Now, let me see why I didn't have that problem when I did it earlier.
If you rotate 1, 2, 3, 4, 5, you end up with 2, 3, 4, 5, 1.
Yeah, that's why they're equivalent.
That's why they're equivalent.
These two cycles.
Yeah.
But it would be nice if it started out.
So when you started off the thing with the dot 2a, you started at 2. Right?
Can you switch back to your code? Yeah, show the code.
Excuse me? Yes.
So when, on 155, when you call self dot 2a, it should be 2, 3, 4, 5, 1.
Oh, yeah. Yeah, the bucket should just be a list of numbers. It doesn't have to be self.2a. It could just be 1, 2, 3, 4, 5.
Actually, there's. What do you mean?
If you want the first element to be 1.
Oh, actually, yes, that's correct. Yes, that's where I made a mistake. This is supposed to be 1 to p dot size. That's what we want. And now this is going to give us what we want. There, good. I was just trying to keep you on your toes to see if you noticed the mistakes we were typing. Okay. All right, so now the next thing we need to do, we have a rotation working, but we now need to be able to handle a multi-cycle permutation. So let's make the next test. And for this one, let's define the permutation on one line because we don't have a lot of space for two columns. So let's say P is equal to P dot from cycles. And let's say, let's have a cycle exchanging 1 and 4, and then another cycle that does 2, 5, 3. Okay? And so then we're going to expect that P dot cycles to equal and then this is supposed to be an array of arrays. So this is the answer that we're expecting to get. And let's see if this works. Doesn't. We got the first cycle with the code that we have, but we didn't get the second cycle. Well, that's obviously the case because we only went through this once. So I think what we need to do to solve this is that after we take each element and place it into one of our cycle objects, we also need to take it out of the bucket. So, and we can do that by using array subtraction, which works like as kind of a set operation. And then, what we need to do is somehow iterate until our bucket's empty. So, why don't we, up here, why don't we put in a while statement and say while the bucket is not empty. And then we're going to have to indent some of this stuff here. So now what's going to happen here? Actually, we probably want the. Excuse me?
Yeah.
Yeah, we want the end to come right here.
Yeah.
So now this is going to keep going around until the bucket is empty. Is there anything else we need to add to that? I think that
Should
might
look
do
in the
it.
bucket
and then
once
we
in a
need to
while.
return.
It should look in the bucket once in a while to see what to do.
Oh, yeah. Where's the
Oh yeah, that's right. That would be a good thing to do. So instead of, well, we do look in the bucket.
Yeah, but
Just
outside
once.
of your loop.
Yeah,
Once
that's,
in the
that
wild.
needs to go in the loop.
Your bucket keeps changing, so that needs to go in your loop.
It's not in the beginning. Yeah.
Let's see. Well, why is that?
Can you run your tests now to see?
Yeah,
what
let's
happens?
run the test and
I'm
see if it
excited
works.
to see the result. Yeah.
It's going to take a while.
Yeah.
Oh.
Oh, do I have an infinite loop here?
Yeah.
Okay. Okay, what did we do here?
How did
So-
it actually die there?
So we start out with
Control
the,
C.
so we start out with the, oh, I see, yes, we need to look in the bucket inside the loop. That's what you guys were trying to tell me.
Yes.
So, that goes there. Does that look better?
Yeah.
Probably.
Okay, let's try.
It looks better, I don't know if it's right.
Let's
there.
try that
It
one.
looks better.
Okay, 17 examples, no failures, very good. Okay? So now the next thing is that typically with these permutations, the way people like to represent the cycle decomposition is they like to remove the degenerate cycles. So in other words, if we have, let's now put P is equal to P dot cycles.
So we really only have 3 minutes.
I realize that. 1, 3. And maybe we'll have 2 is a little cycle on its own. And 4, 5. And then we would expect P dot cycles dot 2 equal, cycles dot 2 equal, and we really only want to capture the 1, 3 and the 4, 5. We don't want to bother with the degenerate cycle because we're just going to assume that anything that's not in an explicitly listed cycle is just going to be mapped to itself in the permutation. Excuse me, and end array. Thank you.
And starter.
What did you run?
You should start the array.
We were asked, saying rapid an array, you just put the heading.
Yes.
Oh.
There you go.
There we are. Okay, so we still are missing something here. P dot cycles 2 equal array 1, 2, 4, 5. What's wrong with this?
Convinced it ran again. But it really did. Okay.
Oh, we just got the one failure. Okay, so we need to get rid of the 2 here.
Still running?
So I think what we can do here at the end is we can just, after we get the cycles, we can just remove the ones that don't have that we aren't interested in. So we could do let's see, cycles dot reject.
Exclamation.
Yeah, exclamation, okay.
Well,
Hmm? You want it
Just-
with or without the
If you
exclamation?
don't need it, because just get rid of your cycles on the next line.
Oh, that's true. Cycles dot reject C, where C dot count is less than or equal to 1.
Let's change those to curly braces.
Excuse me,
yeah.
curly braces are good.